Hi guys, I'm going to go over page 5 in your notebook with you today. It looked like you did a pretty good job on the stuff that I had left for you yesterday. So today we're going to talk about the different temperature scales and how to change between the two of them. So what are the different ways the temperature can be represented? So first of all, temperature, we talked about a little bit the day I was there about kinetic energy. So temperature is a measure of the kinetic energy. So the more kinetic energy that there are in the particles, then the higher the temperature is going to be. So as the temperature increases, then the amount of kinetic energy would increase, and vice versa. Heat now is different than temperature. We talk about them a lot interchangeably in everyday life, but heat is actually the measure of the energy that's being transferred. So heat is more of a quantity, and temperature is more of a representation of the energy. So the heat is going to be the measure of the amount of energy transferred from one substance to another. We talked the other day about how you can't transfer cold, you just transfer heat. So this is what I was relating that to. So you can't transfer cold to something, but you can transfer warm to or away from something. And so that's where the heat flow part comes in. So energy is always going to flow from a higher energy to a lower energy. So higher energy or higher temperature down to a lower energy or lower temperature. Okay, so in other words, if you have hot tea and you add an ice cube to it, cold isn't actually transferring to the hot is transferring away from the tea into the ice cube. So you're actually making things less hot, not making them cold. All right, so then there's the 3 different temperature scales. So we're going to represent those. The first one's going to be Celsius, and the next one is going to be Kelvin, and the next one is going to be Fahrenheit. Now, Fahrenheit we only use in the US, basically, and we only use it really for weather. We don't use it for anything else in science, so it's kind of not really exceptionally useful. But that's the one we're kind of thinking about right now with our cold temperatures. So if we were to talk about our freezing point, that's going to be 32 degrees Fahrenheit, which is what we're used to. I don't know that you even have the boiling point memorized. It's 212 degrees Fahrenheit. So when it's 100 degrees here and it's very, very hot, imagine doubling that. And then those are not exceptionally useful to us. We don't use those at all in science. Again, like I said, just really for weather. All right, so then the Celsius scale is the one we've been using in the lab, using our thermometers and stuff. These are the 2 that are going to be used in science, the Celsius and the Kelvin. The Celsius one, we're going to also go up then to the freezing point there. So our freezing point at Celsius is 0 degrees Celsius, nice and easy to remember. And the boiling point is exactly 100 degrees higher at 100 degrees Celsius. So you can see that a Celsius degree isn't the same size as a Fahrenheit degree. There's 180 Fahrenheit degrees between those 2 temperatures, only 100. So a Celsius degree is a much larger step. Okay. And then the center one is our Kelvin, and this is what you're going to use now when we start talking about gases. All of the representations and ratios related to gases are based on Kelvin. And so Kelvin is the same size degrees as this one. So we're really kind of not even so much thinking about that one. Same size degrees, except now the scale is shifted up. So freezing point is going to be 273 K, and we don't use the little degree symbol. And then same thing, 100 degrees more, it's 373 degrees Kelvin for our boiling point. So those are our freezing points and boiling points as far as the 3 different temperature scales. So then you notice that there's a line down at the bottom. This is what we call absolute 0. It has never been obtained. It's when all motion ceases. So all particle motion, not a single particle motion, and that's 0 Kelvin. So it hasn't existed. We're scientists battling, trying to find it. But if you can imagine then, if these are the same size degrees, that would be negative 273 degrees Celsius. So that's how cold absolute zero is. So all motion stops, hasn't been obtained. But Celsius and Kelvin, these are the two that we're going to be using within science. Okay, these are the ones that are on our thermometers. And this is what we're going to especially use when we do calculations with our gas laws, which is going to be coming up next. So that'll be valuable for you to know. And then to be able to switch between the two of those, if you guys go ahead and turn to table T in your notebook, in your reference table. So that's the one at the back where all the formulas are. To change between Kelvin and Celsius, we just take our Celsius temperature and add 273, which is exactly what we did here, right? So here's our Celsius temperature, we added 273. Our Celsius temperature, we added 273. You don't have to memorize that formula. I mean, you just look it up on the reference table. So if I have the Celsius temperature, I just add 273 to it. If I have the Kelvin temperature, then I would just go backwards and I would do the opposite. So for example, if my Celsius temperature was, let's say 50 degrees Celsius, and I had to change it to Kelvin, the Kelvin is just the Celsius temperature plus 273. Really simple. So I just add those two numbers together. If I'm given the Kelvin temperature, so let's say I have 100 Kelvin and I have to change it to degrees Celsius, well, now I'm plugging my Kelvin temperature in for K. It equals the Celsius plus 273. So then I just do a little algebra to get the Celsius by itself. I subtract 273 from each side and I get my Celsius temperature. Okay.